once again, chapter 11 is about angular momentum, and we really start getting into angular momentum actually in the second section, whereas the previous section was about rolling motion. Now, angular momentum is pretty easy to understand if we already understand translational or linear momentum. We know that for many of these rotational quantities, all we need to do is take the rotational analogy and substitute for what we had with the translational equations. So for instance, linear momentum, P equals mv. In this case, we will use the letter L for angular momentum. L is going to replace P, okay, is equal to, now remember, P is equal to mv. Our rotational analogy for m, for mass, is moment of inertia, okay? And our analogy for velocity, P equals mv, our v becomes omega. Now, just like we had with linear momentum, our angular momentum points in the same direction as our angular velocity. Linear momentum, the linear momentum vector pointing in the same direction as the translational velocity. So when we look at something rotating, and here we have a rotating disk, it's rotating in the counterclockwise direction. So with respect to the z-axis here, if the x and y plane represents the plane of rotation here, both the angular velocity and the angular momentum are going to point in the same direction. Okay, angular momentum. Why is angular momentum important? Well, just like with linear momentum, it is a quantity which is always conserved in a particular frame of reference. So whatever the angular momentum is before an interaction, that will be equal to the angular momentum after the interaction, as long as there are no external torques acting on the system. So looking at angular momentum, we've already said that we can express the angular momentum if we know the moment of inertia and the angular velocity. We can also get this from our linear quantities if we say that the angular momentum is r cross p. Now, this goes back to what we did when we had torque. Remember, torque, which is the rotational analogy for force, was equal to the position vector r cross the force vector F, okay? So we had torque is equal to R cross F. Now we can do the same thing for angular momentum, sorry. Angular momentum is R cross P. And if you think about torque, okay, as being the force that is going to change motion, L is really the quantity that describes your rotational motion. It takes into account the moment of inertia and the actual angular velocity. So again, R cross P is our definition for angular momentum. And again, here are, the two equations, and looking at the vectors, here we have L is R cross P. It allows us to bridge the connection between our linear momentum and our angular momentum, just with this position vector, with this moment vector. And of course, we have torque is equal to R cross F. You can see the symmetry between the two equations there. Now, let's do a simple calculation for a mass moving in a circular path. Usually, when we're describing angular momentum, there can be two components to the angular momentum that are easily identified. One is the angular momentum due to something rotating on its own axis around its center of mass. And the other one can be an object moving around a center of motion. In this case, this ball is moving in a circular path around the z-axis. So here we have L is equal to R cross P. We have a mass of of what do we have here? Okay, well, we're just giving momentum here. We have a momentum of 6 kilograms meters per second. We have a position of 5 meters from the center of circular motion. And when we do R cross P here, 5 times 6 is going to give me 30. And this is going to be in Newton meters seconds for angular momentum. Now, how do I get that? Well, our newtons are kilograms meters per second, okay? So I have kilograms meters squared per second. Newtons are kilograms meters per second squared, sorry. So if I multiply this by meters, that makes my meters go to meters squared. If I multiply it by seconds, 1 over second squared becomes 1 over seconds, and that's how I get my units there. Again, I could have done this a number of different ways. I could have used the determinant to find the cross product. If I were to write this out, I would have I hat, j hat, k hat, and then I would have in the next row, I would have my position vectors here. I would just have an x component, nothing for the y and the z. And then for the momentum on the bottom, I would have, in this particular case, a y component. So the only, part of the determinant that would remain would be the x, the y, and then the z component of that diagonal. And that gives me 30 Newton meter seconds k hat in this particular direction, which means that my angular momentum points in the positive z direction. If I did the right-hand rule for this, I am going counterclockwise, okay? Counterclockwise on this xy plane. And of course, in that particular case, I know that my angular momentum is perpendicular to or normal to the plane of rotation, okay? Going counterclockwise, again, that's going to be the positive z direction. Let's calculate the angular momentum of the Earth. Now, first of all, if I have a solid sphere, I know that the moment of inertia is 2/5 mr squared if the sphere is of constant density, okay? So I'm going to do the calculation right here for our Earth and try to find out what is its angular momentum. So first of all, I start out with the moment of inertia. Now, some of you are already saying, well, wait a minute, you can't do that because the Earth isn't in a homogeneous sphere. It actually is denser in the center. We'll take care of that in a little bit. But again, 2/5 is going to be 0.4. The mass of the Earth is 5.797 times 10 to the 24 kilograms, and it has a radius of 6.37 times 10 to the 6 meters. So I'm going to square that. So I get a moment of inertia of 9.69 times 10 to the 37 kilograms. I'm going to tell you right now, that's too hot, okay? And we're going to reason why that's too hot. Now, if I approximate, this is an approximation because the Earth actually doesn't rotate, exactly once every 24 hours. There's a combined motion of the Earth around the sun, which changes that a little bit. But we get a pretty good approximation here. That omega is 2 pi radians of rotation every day. There's 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. So I get 3,600 seconds in an hour times 24 hours, 86,400 seconds in a day. And that gives me a angular velocity of 7.27 times 10 to the minus 7 radians per second. So my angular momentum is the product of my moment of inertia times my angular velocity, okay? Now, my angular velocity is pointing along the North Pole. That's going to also be the direction that my angular momentum is going. If we think about this, the East Coast rotates toward sunlight. So the sun rises in the east, it sets in the west. So looking down from the North Pole, we would see that's rotating counterclockwise, okay? So this is our direction. By the way, The result, the reason why we have clockwise going in the other direction is the original sundials. If you think about how the Earth was rotating with respect to the sun, as the Earth rotated counterclockwise, the shadow on the sundial would rotate clockwise. And that's why the faces on the clocks we have for analog clocks rotate in that particular direction. They want to preserve that movement. Okay, so L equals I omega. We multiply these two together, and we get that the angular momentum of the Earth is 7.05 times 10 to the 33 meters squared kilograms over seconds. And that, again, as I said, is far too large. That's because what's happened is with the Earth is it's differentiated. A great deal of its mass settled toward the center, where the iron, being of much higher density, being close to the center, actually has a lower moment of inertia than if it were sitting at the equator. So what happens here is, because we don't have a homogeneous density, my moment of inertia is too high, and that, in fact, makes my angular momentum too high. So let's try to get a better estimate for the angular momentum of the Earth. Now, the problem is each part of the Earth has a different density. The inner core is the densest. Because it's compressed and it's iron, it's going to have a very, very high density of 12.8 to 13.1 grams per centimeter cubed. Or if you want to convert that to SI units, that's going to be 12,800 to 13,100 kilograms per meter cubed. The outer core, also made out of mostly iron, has a very high density. It's not quite as compressed as the inner core. And then the lower mantle and the upper mantle also have very high densities. We know at least the upper mantle has a large amount of iron and magnesium-rich silicates, such as olivine, and therefore a very high density. And then the crust, which contributes the least to the moment of inertia, because it's so thin, it doesn't really have very much volume and therefore not much mass, is going to be up there. So again, this figure is going to be very high. How do we find the moment of inertia when we have this stratified layer? Well, if we did this properly, we would have to integrate over the inside. Now, here is the moment of inertia, r squared dm. If we do density as a function of radius, we would integrate it this way, because mass is going to be equal to our density times our volume. So an infinitesimal amount of mass is a density times an infinitesimal volume. So here's what we have to integrate. Now I can do this numerically and come up with something that's pretty precise, but let me instead integrate it such that I'll do the inner core, the outer core, the mantle. I'm going to ignore the crust. It's just too thin to really contribute very much to this. And I can, do this type of integration. I can actually simplify this. This is not that bad. We have an inner core, then we have a hollow sphere, which is our outer core. Then we have another sphere, which is our mantle. We can do this. It's just very difficult to integrate. It's not. It really isn't. You just take the inner radius and the outer radius. But I can actually cheat here and do a moment of inertia as if the entire Earth were the density of the mantle, and add on top of that the effective difference between the outer core and the mantle, and integrate that, and then take the effective difference between the inner core and the outer core. And we're sort of stacking them in this direction. So I have a sphere, and a sphere. And when I do that, I can take that the moment of inertia for each sphere is 8 pi times rho arc to the 5th over 15. We've done this integral already when we did moment of inertia. But again, these are effective densities. Okay, these are effective densities. When I do this density here, it's really the density of this difference in density over this difference in density in taking this. So we're going to go ahead and do this. So the inner core has a greater density than the outer core. Basically, it's 1,500 kilograms over meters cubed greater in density. So I'm going to integrate for its radius and come up with this is its contribution beyond what the outer core mantle would provide if they were if the inner core were part of that. So this is the contribution, the excess contribution of the inner core over the outer core of the mantle. Here's now the contribution of the outer core over the mantle. Okay, the outer core is also denser. Okay, this should be 6,700. I do get it right down here. And then finally, putting everything together, doing the effective moment of inertia of the mantle. If the outer core and inner core weren't there, we can then add the excess outer core moment of inertia and the excess inner core to that. And we get a new value of 9.29 times 10 to the 37 kilograms meters squared. So 9.29 times 10 to the 37. Let's go back to what we had previously. Previously, we had a larger value for that moment of inertia. Okay, and okay, so it doesn't actually decrease the moment of inertia as much as you would have thought, but with this new value, if we multiply this times by the angular velocity, we get 6.8 times 10 to the 33, as opposed to 6.8 that we have before. Sorry, I'm scrolling back here. 7.0, 7.0. So, a better correction for the moment of inertia. Again, understanding that most of the mass of the Earth is contained in the mantle, but we have a denser core, which means that we can't use can't treat the Earth as a homogeneous sphere when we're doing this calculation. Okay, orbital angular momentum. So the Earth has angular momentum due to its spin. It spins on its axis. It'll have angular momentum associated with just being on its axis. But we also have to remember that as the Earth orbits the sun, there is an angular momentum associated with that orbit. This is going to be L equals R cross P. And if we look at this, we can say, well, we can change this to R times P sine theta. Theta represents the angle between R and P. For the most part, we can say that theta is pretty close to 90 degrees. The sun is in an elliptical orbit. So this does vary a little bit, but we also have to remember that R is going to vary. So if we take R to be the average distance, P to be the average momentum of the sun, of the Earth around the sun, and take sine theta to be 90 degrees, we get RMV. That angular momentum is going to be conserved as it goes around. It's really the reason why Kepler's second law holds, that we speed up closer to the sun and we slow down further from the sun, because as R gets smaller, our momentum has to increase to conserve angular momentum. So again, RMV, here is our radius of our orbit. Here is our mass. Here is our average speed. And we get 2.7 times 10 to the 40 kilograms meters squared over seconds. This is significantly greater than our spin angular momentum. The angular momentum of the Earth going around the sun is 2.7 times 10 to the 40, whereas if you remember, we were 6.8 times 10 to the 33 for the spin angular momentum. So it's much, much greater in terms of the orbital angular momentum of the Earth going around the sun. Now, with Newton's second law, it is important to remember that anytime we have torque on a system, that torque is going to change the angular momentum. Just like F is equal to dP dt, here we have torque is equal to dL dt. And any torque acting on a system is going to either increase or decrease the angular momentum. If this torque is constant, we can change this to the change in angular momentum divided by the change in time is equal to the net torque on the system. Now, again, looking at the orbital angular momentum of the moon this time around the Earth, it's equal to 3.85 times 10 to the 8 meters. That's the radius of its orbit, times its mass, much smaller than the Earth. It's 7.34 times 10 to the 22 kilograms. And then we multiply it by its velocity around the Earth. Here we get an orbital angular momentum of 2.9 times 10 to the 34 kilograms meters squared per second. But at one time, the moon orbited much closer to the Earth. It had less orbital angular momentum. What happened? 3.5 billion years ago, the moon was a lot closer to the Earth. Well, let's go back to what we said about tides and torques before. Remember, we said that about 3.5 billion years ago, the Earth rotated on its axis once every 9 hours instead of once every 24 hours. Okay, this is a pretty significant change, 2.5 times the amount of orbital angular momentum for the Earth. What's happened here is that the torque on the Earth due to the moon has slowed down our spin angular momentum. Likewise, the torque on the moon by the Earth has increased the angular momentum, and that's causing the moon to move away from the Earth. So as you can see right here, we have conservation of momentum in a system, conservation of angular momentum of a system, where the Earth is sacrificing some of its angular momentum to the moon via the torque provided by the tides, okay? And the moon is gaining orbital angular momentum. Now, the moon will never break free of the Earth. This torque becomes less and less as the two bodies get further and further away. So eventually what's going to happen is that the torque is going to be so small that there'll be hardly any change. In fact, today, we're up to 24 hours a day. For a day, we're getting to the point where the torque is much, much less today than it was 3.5 billion years ago. Okay? In about 50 billion years, the Earth will slow down enough to rotate in sync with the moon's orbit. In fact, this is called tidal locking, but we know that this will not happen. In fact, 5 to 6 billion years from now, the sun will blow out to become a red giant. And even if it doesn't destroy the Earth, it will probably disrupt the Earth-Moon system enough that this tidal locking won't have a chance to take place. But again, very important to understand that whenever we put a torque on a system, that torque will change the angular momentum. Here we have a simple system of a diver going off of a diving board. As she leans back, her center of mass is over her base. Her base creates angular momentum here via torque, okay? Our torque is equal to her weight. Her weight is equal and opposite to the normal force from the board. That pushes up 0.4 meters. Again, we do our line of action here. The center of mass, that's where the force is on here, causing her to rotate here. Here we have the board pushing up on her. And again, we can calculate from this that the moment of inertia of this diver times this angular acceleration is going to be equal to the torque, the force from the board times this distance. And again, we see that as she's pushing off the board, she is going to receive torque, which is going to result in a angular acceleration of 33.3 radians per second squared. So again, she has a weight of 500 newtons. She creates a reaction force by pushing down on the board of 1,000 newtons. Okay, what is her angular acceleration? Now again, if we look at here, the center of mass is right here. We want to see how much torque is created, by that center of mass, around that center of mass. 1,000 newtons acting as the normal force right here at a distance of 0.4 meters is going to give her an angular acceleration of 33.3 radians per second. I apologize. I was saying that the weight was giving her the torque. It's actually she's pushing down. So she's increasing it beyond just what the normal force would be. She'd still get angular acceleration here if she just leaned back and let her weight passively do this. But because she pushes down with as much force as her weight is pushing down, she's going to actually increase the angular acceleration even more. What is her angular velocity if she pushes off the board for 0.15 seconds? Here we have our angular acceleration. I could do this one of two ways. If I said that the torque is constant, which it has to be if our angular acceleration is constant, I could take the 0.4 times 1,000, which is 400 Newton meters of torque, and multiply that times 0.15 seconds to get my angular momentum change, and then use that to find the angular velocity. But it's actually easier once I find the angular acceleration to calculate the angular velocity change based on that. So I get 5 radians per second. And what is her angular momentum as she's doing her backflip? Her moment of inertia, we need to know her moment of inertia. Her moment of inertia when she's stretched out like this, what we call the pike position, is 12 kilograms meters squared. We multiply this times her angular velocity, and that gives me 60 kilograms meters squared radians per second. And again, going back to this torque right here, 1,000 newtons times 0.4 meters. If we go to that once again, 400 Newton meters times 0.15 seconds, we'll also get an angular momentum change of 60 kilograms meters squared radians per second. In quantum mechanics, we quantize angular momentum. This leads to essentially what we have in the periodic table. If we look at what is taking place here, we have the angular momentum of an electron around the nucleus. This is what we call orbital angular momentum again. But also the electron acts like it's spinning on its axis, even though it's more of a point. It also has spin angular momentum. So when we look at the total angular momentum of an electron in orbit, each electron has a spin angular momentum. This is quantized. It can either be spin up or spin down. And an orbital angular momentum, which goes by R cross P, which is the classical momentum of the electron around the orbit. So we're looking at the electron in terms of its classical picture. The classical picture, there would be no, restriction for what the spin could be. In quantum mechanics, it can be spin up or spin down. In classical mechanics, the orbit is not restricted. In quantum mechanics, our orbit is quantized. So when we look at this, we know from chemistry, there's a principal quantum number. There is a angular momentum quantum number, which, basically, if we look at the n, our n equals 1 is the closest orbits to the nucleus. N equals 2 is the next one, then n equals 3 goes all the way out to infinity. Okay? Of course, the electrons always fill up the ground states first. The L right here, this angular momentum, this orbital angular momentum, results in two quantum numbers, okay, from the orbit. There is the angular momentum quantum number L, but there's also the magnetic quantum number ML. So L results in S, P, D, F orbitals, okay? So L equals 0 is going to be your S orbitals, P is going to be L equals 1, D is going to be L equals 2, your F is L equals 3. And then your magnetic orbital numbers talk about how these orbits are actually aligned with the z-axis, and these are quantized also. They go from negative L all the way up to positive L. So that is why in the S orbital, you can only have a spin up or spin down. It's 0. So ML is always going to be 0 here. For your P orbitals, ML can be -1, 0, or 1. So you have 3 pairs of electrons here. Your p orbital can fit 6 electrons. And then your D can have ML from -2 all the way up to 2. That gives us 5 pairs or 10 electrons. F, of course, we have 4 more than that. Finally, our spin quantum numbers are quantized, so you can have spin up or spin down. And that allows us in the S orbital, L equals 0, ML equals 0. We can't have 2 electrons in the same orbital state, so one's going to be spin up, one's going to be spin down. And again, if we picture our magnetic quantum numbers, here is our p orbital. We can see that it can be oriented with the x-axis, the y-axis, or the z-axis. And this gives us, well, that's probably not a good way of putting this, ML, +1, ML -1, or ML equals 0. Here's what, in quantum mechanics, the orbitals look a little bit more like this. We know in quantum mechanics that the electron's not physically orbiting the way that we think of in terms of classical orbit. It's actually a matter wave. But again, you can see how the different quantum numbers result in different shapes of these orbitals. Here's our s orbital. Here are our p orbitals. Here are our d orbitals. Here are our f orbitals. And gets a little complicated, but these are all from classical values. So again, really taking the electron, taking the electron's orbit and quantizing both the angular momentum from the spin and the angular momentum from its orbit results in the chemistry that we see, results in the way that electrons will bond with one another, or produce bonds. Atoms bond together to form molecules. But it all comes back from classical physics, where we get these different numbers.